The Sun is a G2V-type spectral main sequence star, which means it is in its adult phase, converting hydrogen into helium. But despite studying it for millennia, it still hides secrets that defy the laws of thermodynamics we know on Earth. The greatest of these mysteries is the coronal heating problem. While the solar surface, the photosphere, records about 10,000 degrees Fahrenheit, the outer atmosphere, called the corona, reaches an incredible 3.5 million degrees Fahrenheit. Imagine moving away from a campfire and suddenly feeling the air getting thousands of times hotter. This defies common logic. To understand this, we need to talk about magnetism. The Sun is not solid, it is composed of plasma, which is the fourth state of matter, where the gas is so hot that electrons separate from atoms, creating an electrically conductive fluid. When this plasma moves, it generates magnetic fields through a process called the solar dynamo. One of the most accepted theories for the heat of the corona is nanoflares, small explosions of energy caused by what we call magnetic reconnection. Magnetic reconnection occurs when magnetic field lines in the plasma break and reconnect violently, converting magnetic energy into heat and kinetic energy. It is a direct application of Ampere's law, which relates magnetic fields to the electric current that produces them. Historically, we owe much to Eugene Parker, an astrophysicist who, in 1958, predicted the existence of the solar wind. At the time, his idea was rejected, but today we know that the Sun blows a constant stream of charged particles at speeds exceeding 1 million miles per hour. However, we still do not know exactly how this wind is accelerated so brutally right as it leaves the star. Another point we still cannot answer precisely is the duration and intensity of solar cycles. Every 11 years, the Sun's magnetic field completely reverses. The North Pole becomes the South and vice versa. This phenomenon was first systematically observed by Heinrich Schwab in 1843. Although we know it happens, current mathematical models still fail to predict whether the next cycle will be devastating for our satellite communications or if it will be a period of calm. If we descend below the visible surface, we enter the convection zone, where plasma rises and falls like boiling water in a pot. But it is in the core, at about 27 million degrees Fahrenheit, where the real magic happens. Nuclear fusion. Here, the Sun converts 660 million tons of hydrogen into helium every single second. This process follows Einstein's famous equation, where energy is equal to mass times the speed of light squared. A small amount of mass lost during the fusion of hydrogen nuclei is transformed into a colossal amount of energy. Without this calculation, we would not understand why the Sun has been shining for 4.6 billion years without burning out. However, a modern and frustrating dilemma arises here: the solar abundance problem. For decades, models of helioseismology, which is the study of the Sun's vibrations, acting as if we were using sound waves to take an ultrasound of the star, agreed perfectly with chemical models. But in 2005, new spectroscopic analysis techniques, led by researchers like Martin Asplund, suggested that the Sun has much fewer heavy elements, such as oxygen, nitrogen, and carbon, than we previously thought. This discrepancy created a rift in science. If the chemists are right, our physical models of how energy travels from the core to the surface are wrong. If the physicists are right, our way of measuring the chemical composition of other stars in the universe may be based on false premises. As mentioned earlier, plasma is a complex conductor, and perhaps our understanding of its opacity, the ability of solar material to block or let radiation through, still needs new mathematical calculations. Speaking of deep mysteries, we have the solar neutrinos. These subatomic particles are ghosts that pass through matter almost without interacting. In the past, we had the neutrino problem, where we detected only a third of what the theory predicted. This was solved by Raymond Davis Jr. and Masatoshi Koshiba, who proved that neutrinos change flavor on their way to Earth, a discovery that earned them the Nobel Prize in 2002. But questions remain. What can neutrinos tell us about sudden changes in the core that light would take 170,000 years to show us? Yes, the light you see today was generated before the emergence of Homo sapiens, navigating a labyrinth of collisions inside the sun until it finally managed to escape. While the sun seems like a constant and unchanging presence in the sky, it is a restless beast. One of the most terrifying and least understood phenomena are coronal mass ejections, or CMEs. Unlike solar flares, which are flashes of light, CMEs are giant bubbles of magnetic plasma launched into space at speeds of up to 7 million miles per hour. If one of these hits Earth directly, it could fry electrical grids and destroy the satellite infrastructure we totally depend on today. The largest recorded event of this type was the Carrington event in 1859, named after astronomer Richard Carrington, who observed the initial explosion. At that time, the most advanced technology was the telegraph, and the wires actually threw sparks. The question we still cannot answer is, how big can a superejection be? Recent studies of other sun-like stars show explosions 1,000 times more powerful. We don't know if our sun is capable of such violence or if we are protected by some internal mechanism we haven't mapped yet. These explosions are governed by magnetohydrodynamics, an area of physics that studies the dynamics of electrically conducting fluids in magnetic fields. It is a combination of Maxwell's equations, which describe electromagnetism, and Navier-Stokes equations, which describe fluid motion. Basically, solar plasma behaves like a liquid carrying invisible wires of electricity and magnetism. Another mystery puzzling scientists is the so-called Maunder minimum. Between the years 1645 and 1715, sunspots, which are cooler regions of the photosphere caused by intense magnetic fields that inhibit convection, practically disappeared. This coincided with the Little Ice Age in Europe. As mentioned earlier, the solar cycle lasts 11 years, but the Maunder minimum suggests there are much larger cycles, spanning centuries, that can drastically alter Earth's climate. We still cannot predict when the next great magnetic silence will occur. Scientists like Valentina Zarkova have proposed double magnetic wave models to try to explain this, but the truth is that the sun's interior remains opaque to our long-term predictions. We are only beginning to understand how long-term solar variability translates into climate change down here, a crucial field of study to separate human impact from the natural variations of our star. Every story has an end, and the sun's is no exception. Currently, it is in the middle of its life, having consumed about half of its hydrogen fuel in the core. In approximately 5 billion years, the sun will undergo a dramatic transformation. When the hydrogen runs out, the core will contract under its own gravity, becoming so hot that it will begin to fuse helium. This will cause the outer layers to expand violently, transforming it into a red giant. This process is explained by Newton's law of universal gravitation, where the attractive force between masses tries to collapse the star, while radiation pressure from nuclear fusion pushes outward. It is a delicate balance called hydrostatic equilibrium. When the fuel changes, this balance is broken, and the star changes size to find a new point of stability. As mentioned earlier, the expansion will be massive. The sun will grow large enough to swallow Mercury and Venus. The fate of Earth, however, is still one of the great what-ifs of astronomy. While the sun loses mass through powerful stellar winds, its gravitational pull weakens, which could, theoretically, push Earth's orbit further away. However, the drag from the outer layers of the solar atmosphere might be strong enough to pull us in. Even if Earth is not swallowed, life as we know it will end much sooner, in about 1 billion years, as the gradual increase in solar brightness, about 10% every billion years, will cause a runaway greenhouse effect, evaporating our oceans. After the red giant phase, the sun will eject its outer layers, creating a beautiful planetary nebula, leaving behind only its dense, hot core, a white dwarf. This object will be roughly the size of Earth but with the mass of half the original sun. A teaspoon of this material would weigh tons. What we still cannot answer is the detailed, fine chemistry of these nebulae and how they enrich the interstellar medium to form new stars and planets. The sun is our past, our present, and the architect of our end. Studying it is not just scientific curiosity, it is a matter of planetary survival. Every probe sent, like the Parker Solar Probe, brings us closer to understanding the force that gives us life and that, one day, will take it back.